Hello, we talked about energy and we talked about kinetic energy and potential energy. We explored all of that part of thermodynamics. But remember, the definition of thermodynamics includes the study of energy and its transfer in a system. The system that we'll be talking about is the atmosphere and parcels of air in the atmosphere and the surface of the Earth. So we haven't talked about the transfer. We're going to talk about the transfer of latent energy first because it's so important to the formation of clouds. Let's go through that. We just talked about latent energy, and now we want to know how we transfer latent energy. And you might say to yourself, well, wait a second. Didn't we use up all of the latent energy during all of that boiling in here? I mean, it was a really long boiling phase. We used a lot of energy in that boiling phase. Didn't we use it all up? And conversely, when we go into melting, don't we use up a whole lot of energy melting? Well, actually, no, we can't use up energy. It's actually part of the first law of thermodynamics that the first law of thermodynamics states that energy can't be created or destroyed. It can simply be transferred. And that sounds an awful lot like another law that you might know. And that is the law of conservation of mass. That in a chemical reaction, mass can neither be created nor destroyed, but conserved. And conserved is pretty similar to transfer. And these do have things in common. And they have mass in common. And they have matter in common. So they're very closely related, but we need to look into them a little bit further. When we're thinking about transferring latent energy, what I can tell you is that the latent energy that we put into all of these water bonds while we were at the boiling point, right around 212 degrees Fahrenheit or 100 degrees Celsius, all of that energy went into the higher phase. All of that energy went up and hid in the water vapor. And now the water vapor that is in the air from the kettle is containing all of that energy. That's a lot of energy in water vapor. And we'll be talking about the power that that energy has throughout the course. In addition, when we talk about melting ice, all the energy that went to break the ice bonds in that ice went into the liquid and is stored in the liquid now. And that is why you know that liquids have more energy than solids, and gases have more energy than liquids. It's because it is a latent energy transfer. Now, if we know where the latent energy transferred to, where did the latent energy transfer from? How did it get there? Because it can't be created nor destroyed. And since we know that there is a lot of energy in the environment, that's the energy that we're going to use. For instance, you took all those ice cubes out and you put them on the counter. Well, the counter is warmer than the ice cube. And so the counter transfers its energy into the ice cube, and the ice cube absorbs the energy. As the counter transfers its energy into the ice cube, the counter loses energy. It transferred it out. The counter cools. And that makes sense. And conversely, when we are boiling water, the kettle transfers its hot energy to the water. And that makes sense because the kettle is being heated. And in transferring its energy to the water, the kettle cools. Now you might say, whoa, that kettle is not cool. And it's not. That kettle can definitely burn your skin if you don't have a pot holder. But that kettle is not at 212 degrees or 100 degrees Celsius. That kettle did not catch fire. On the other hand, when all of the water is boiled out of the kettle, that's when you've got a problem. That's when the temperature of the kettle material will really increase dangerously. And it can even damage the metal, and the metal could fail because the kettle is no longer being cooled by this transfer of energy. So that's a fact that metal melting is a cooling process, and conversely, evaporation is a cooling process as well. It is cooling to the environment that is delivering the energy into the system. Keep that in mind, and let's keep going. Latent energy in you, let's make it personal. When you get out of the shower, you get chilly pretty quickly. There's a reason for that, obviously. You're stepping out of the shower and the water is evaporating off of your skin. That water that's evaporating off of your skin needs energy to evaporate. It takes that energy from your warm skin. So your skin transfers energy to the water. And in transferring energy to the water, your skin has a lower energy now. Your skin feels cooler. At the same time, the energy that went into the water that's sitting in droplets on your skin didn't change temperature. So that sounds very similar to the boiling that did not change temperature as well as it vaporized. In addition to that, we can look at another example. You're hot and sweaty. It's just another way to put water droplets on your skin. And in the same way, the sweat will absorb the heat from your skin, making your skin have lower heat. And as your skin has lower heat, it will feel cooler. As your sweat is absorbing that energy from your skin, the sweat is not changing temperature, but it will gradually evaporate off and leaving your skin with a lower energy level that feels cooler. In addition to that, we can talk about latent heat transfer in the atmosphere. Let's talk about the ocean and vaporization from the ocean. The ocean and the surface water will absorb energy from the atmosphere from the sun. In absorbing energy from that atmosphere, it makes the environment a little bit cooler. Then that energy is absorbed by that water that gradually vaporizes off into water vapor. And the environment around the water, the air around the water, feels cooler. Which is part of the reason why you can get a cool sea breeze in the hottest parts of the summer. But we'll talk about that a lot more soon. Evaporation cools the ocean surface and cools the environment right around the ocean surface. Now, these phase changes can happen sequentially or all at once. So a solid can absorb a dramatic amount of energy and move directly to a gas at some times. And I'm going to move this up so you can see it a little bit better because there's two examples. One is dry ice, which is solid carbon dioxide that under the right conditions can go directly to gas. There's no liquid involved in that. It goes right from solid to gas. Another example is Vicks VapoRub, one of my all-time favorites. It's a solid that you put on your throat, but it sublimes, that's the word for this process, it sublimes immediately to a gas. It releases a tremendous amount of cooling to the surface because it is absorbing so much heat away from your skin. All right, your skin feels cooler as a result. Now, latent energy transfer can also reverse. And instead of absorbing energy from the environment, latent energy transfer can release energy to the environment. And in releasing energy to the environment, it will do the opposite. It will warm the environment. So previously we had talked about energy being absorbed from the environment and leaving the environment cool. Now we're talking about energy releasing to the environment and warming that environment. Let's give some examples. Water vapor, as you know now, is loaded with energy, and water vapor is invisible. And so this here is not water vapor. And we were just talking about the kettle and everything else. But guess what? If you can see it, it's not water vapor. Water vapor is invisible. If you can see it, it's condensed, hot liquid water. So this actually went through a phase change right after a phase change. Let's explore it a bit more. Potential energy, as you know, in water vapor is huge and so important to our study of meteorology. In fact, that cloud there has the potential energy of several atomic bombs. Amazing. It's just over a much wider area. We'll talk about that when we talk more about cloud formation. Let me move this down and we can explain it a little bit more. This is relating latent energy and MOOS. So heat energy is released to the environment from the warm breath of the moose. The warm vapor transfers its energy to the colder air. The warm vapor has lost some of its energy. It's lost some of that energy, and now it doesn't have as much energy to have that water vapor so spread out. Those bonds are starting to bond back into water. It changes the gas to water droplets in air. That water droplets in air is steam. So the condensation actually released energy to the air, and the condensation warmed the air around that moose as the steam itself is actually cooling from water vapor. Here's another thing to think about. You have and this applies to summer really well, you have a glass of soda out, and it has a couple of ice cubes in it. And it's a very dry, warm day, which is rare in New Jersey, but it's a dry, warm day. And then on another day, you have that same glass with the same ice cubes, but it's so humid. It's hot and it's humid. So which glass is going to warm more rapidly? The glass that's in the dry environment or the glass that's in the moist environment? Think about it. I'm going to move this out, and I'll explain it to you a little bit. Think about it a bit. You might want to stop the video. But the warm, moist air has water vapor, and you know that water vapor has a lot of energy. It has energy to release to the environment when the vapor condenses. The vapor is going to condense on the outside of the container. The vapor is going to release that energy to the environment. That environment is going to include the soda inside the glass. So the soda glass that is exposed to the warm, moist air is going to warm more quickly and lose its fizz more quickly too than the glass that is associated with the warm, dry surroundings. Okay, this has a couple of layers to it. Now, that freezing can warm the environment too, and that makes no sense, you say. That makes no sense? And the extremes of this never seem to make sense until you think about it again. And we're going to do it in lab. But have you ever been near a freezer exhaust vent? What's it exhausting? It's exhausting hot air. And if that doesn't convince you, we're going to talk about this more in lab to get a better feel for it. I think that's the end of this. Oh, actually, I have one more. You can go directly from vapor to ice as well. And we'll talk about that when we talk about condensation. So you'll see that. Now, you won't see that in the lab, but you will see liquid directly to ice. And I look forward to showing it to you. Take care.